Sir,
Yes.
so should we submit the hard copy of scholarship to college, sir?
Uh, that whatever the copy you are given, no.
We didn't give anything, sir. Like we have applied online. Should we
Okay.
submit that?
No. Actually, that Usha Rani is the SSP representative. She need a document. Maybe you can send hard copy or soft copy to her. Okay.
Okay, sir.
Right. Uh, right. So what I will do, I will. Okay. Fine. This kind of molecules, more particularly overcrowding. See, for example, hexacene, pentacene, and this is benzophenanthrene and phenanthrene. If there is a substituents, so more particularly bulky substituents, and these molecules exhibits optical activity because of molecular overcrowding. And these two are terminal benzene rings are in different phase. So maybe you can observe that when a left hand, okay, left hand finger, it is rotating in clockwise direction, that is called P. Right hand finger, if it is rotating in anti-clockwise direction, that is called M. So overall, what you need to remember, P is nothing but a R, M is nothing but a yes. That's what you need to remember. So this moiety exhibits P configuration. This one is M and this one is P. So, and I will take a few more examples to assign M and P to the molecules. So in that I will explain how you can decide the whether the compound is M or P just by comparison with the R and S configuration. So look here. So in a crowded molecule, if there is a priority is moving from A to B, B to C, C to D. So what it means? It will be moving in a clockwise direction. So if that is the case, it is called P. Okay. And similarly, A to B, B to C, C to D. So this is again, it is moving in a anti-clockwise direction. It is called M. And uh, and then, so let's take Aline case. So this is the one is Aline one. And here, you know that you are familiar to convert this into a this format. That means nearer groups take the priority compared to the far groups. And when you are converting, these are vertical groups and these are horizontal groups. Okay. So if it is a vertical, you can write this chlorine here. This is the one, and this hydrogen here. And when you are viewing from this side, H is coming on the left hand side. That is the H is this. OCH3 is this one. Then afterwards, once you know that, and you know that the nearer groups that takes priority. That is the reason this is 1, this is 2. That means this is 1, this is 2. And between these two, this takes 3. That means this is 3. That means it is moving in a anti-clockwise direction. That is the reason it is having S configuration. S is nothing but a M. That is how you can design. Otherwise, you can also give numbering. So this is the 1, this is the 2. So that means it is moving in this direction. So this is nothing but a what is called as anti-clockwise direction, and this is M. So let's take one more example here. So when the chiral axis is passing through this carbon atom, and you know that this is the wedged one. Always wedged one will be the horizontal groups, and the planed one, plane representation is the one is called vertical groups. And vertical groups, they take the priority. You can convert vertical groups are OCH3 and then H. So this is 1, this is 2. And these are the horizontal one. When you are viewing from this side, CH3 is coming on the left hand side. That is this. So then it will move from here to here, here to here. That means it's a R configuration. Then it's called P. Okay, so similarly you can take one more example, but here the chiral axis is moving from this carbon atom to this. So you can, this is the wedged one is always a horizontal one. So that is the reason. And when you are viewing from here, the CHO group is on the left hand side. That is the reason this is left hand side. These are vertical, OCH3H. So 1, 2, 3. So that means it's a clockwise direction and it is P. Okay. So then, right. So here the numbering. So numbering you should start from this oxygen. 1, 2 and then 3. So that is the reason this is a clockwise direction. Numbering from this carbon is not good. So numbering from this carbon, this oxygen is good. Why? Because you are viewing from this side and these groups are nearer groups. These are far groups. That is the thing you need to correct it here. So then with this, I will go to the next slide. Oh, next slide. All right. So here I am taking few more. This is ANSA compound. These two are also ANSA compounds. This is one more moiety we are taking. So here what you can observe that a substituent is present here. That is the reason this carbon will be the pilot carbon, and this is 1, this is 2, this is 3, this one is 4. So and then it is moving in a clockwise direction. So that is the reason it's called, and also it's called P. And similarly, when you are taking this group, so you know that substituent is here. So because the substituent is present here, then this carbon will be the pilot carbon and this will be the 1, 2, 3, 4. So you know that there is a movement like this. That means it's a clockwise direction. So clockwise direction is called P. Similarly, what you can observe here, when you are giving priority to here, between two, one is isotope of oxygen, another one is based on the molecular mass of the oxygen. So this oxygen 16 is the normal one, oxygen 18 is the isotope one. So, but here this takes the first priority. This is 1, this is 2, and this one is 3. So you know that it is moving in a anti-clockwise direction, and it is called M. Okay. So this is how you can find out the M and P to the chiral compounds. So let's look into the one more moiety. It's called cyclooctane. This is not ANE, it should be E. Okay. So that means this is E. More particularly, this is E. Okay. This is called E, octane. Okay. So then, so you know that this is cis cyclooctane. So cis, why? Because it is cis, CH2 group is this way, CH2 group is this way. That is the reason it's called a cis cyclooctane. And cis one is achiral. This is not a chiral compound. When you are writing cyclooctane in a trans form, so this will be the one isomer, and this one will be the another. So these two are called enantiomers. Of course, these two also is called enantiomers. So if you want to know that R and S configuration, so this carbon takes the one, this one is 2 and this one is 3. What it means? It means that it is moving in a anti-clockwise direction. That is the reason it's called S. So similarly, you can write the mirror image of this one. So mirror image of this one is this. So and here the numbering you should start from this carbon 1, 2, 3. That means what it means? It means that it is moving in a clockwise direction. That is the reason it's called R configuration. So these two forms are called chair forms. Okay, and these two forms is called half chair. Okay, otherwise twisted chair. Okay, twisted chair is called. Anyway, more about the conformation we will discuss maybe now onwards. So these two are conformational isomers only, but again this is S configuration and this one is R configuration, and these two are chair conformation, and these two are mirror images to each other, and these two are enantiomers. And of course these two also enantiomers. And what is here important thing you need to remember, this is a these two representation is called a twist cyclooctene. This is the chair cyclooctene, and more particularly these two are trans. Why it is trans? Because the bulky group is two bulky group. This is one CH2, this is another CH2, are away from the they are away, not adjacent. So that is the reason this one as well as this one is trans. Okay, so if what maybe in terms of words we can say that transcycloalkane is an example of planar chirality. The two trigonal carbon atom directly attached to them are in a plane, and polymethylene bridge is queued in a 3-dimension. Trans-cyclooctane is the smallest ring which can accommodate the double bond, and the two conformations are possible which are mirror images to each other. The interconversion of two enantiomers which require a swinging of tetramethylene chain over and below the plane. The plane of trigonal carbon is opposed, and the angle strain that is strain, and therefore two enantiomers are separated. Trans-cyclooctane is stable at room temperature. As the ring size increases, that means if there is a more number of CH2 chain increases, the energy barrier decreases. So because of that, what will happen? Trans-cyclonanene. So that means one CH2 more compared to the octane. It is stable at minus 80 degrees centigrade. This is not 800, it is minus 80 degrees centigrade. And similarly, trans-cyclodecene, so 10 carbon containing one, is highly mobile and do not show isomerism. So this is about the double bond containing chiral compounds. So with this, I will go to the next slide. So maybe next slide is onwards is about the conformational analysis. So conformation. Then what is conformational analysis? Suppose if two different three-dimensional arrangements in a space of atoms in a molecule are interconvertible merely by the free rotation about the bonds, they are called conformations. See, for example, if they are not interconvertible, they are called configurations. And configuration represent the isomers that can be separated. Then more particularly, what is conformations? Conformations represents conformers. So then what are conformers? Which are rapidly interconvertible. Conformers which are rapidly interconvertible and the non-separable. The terms conformational isomer and rotamer both are same. So let's take an example. I think you are aware about this example. It's called ethane. I think you are aware about the Newman projection formulae. So this is the ethane. And when Newman projection for this kind of Newman representation is called eclipsed form. So because of these two hydrogen interaction, and this moiety is little or unstable because of when it compared to the staggered form. Here there is a distance, more distance between this hydrogen and this hydrogen. So, and this staggered form is more stable compared to eclipsed form. And this is the kind of representation of Newman conformational methods of representation of ethane. So when eclipsed form is rotated at 60 degree, we will end up with staggered form. Staggered form is more stable compared to the eclipsed form. And we will tell you why the staggered form is more stable compared to the eclipsed form by taking uh, maybe in a later slides. So before that, what we will do, we will also discuss the Newman conformational methods of representation of butane. So butane means CH3, CH2, CH2, CH3. So let's take that. This is the one is the butane, and this one is called eclipsed form. You can observe that CH3 and CH3 are on the eclipsed one. And because of these two bulky groups, because of these hydrogens, and this will have a unstable one. And here also there is a Pfizer strain due to the hydrogen and hydrogen, this hydrogen and then CH3 bulky groups, more particularly hydrogen of CH3 groups. So this one is unstable. Overall, you need to remember that eclipsed forms are unstable compared to the other one. This is again, it's called synclinical. So that means a what is that? A rotation. Okay, one of the carbon is rotated to this form, and this is called synclinical. And here you can observe that there is a distance between the two bulky groups. Okay, so that is the reason it's a little less stable, but not the most stable. It's a skewed form. It's also called as synclinical. So we can suppose what is called as, if this CH3 is moving like this, if CH3 is moving and coming near to this CH, then it's called anticlinical. So what you can observe here, CH3 is here, one more CH3 is here. Okay, so this kind of representation is anticlinical. Again, this is also a less stable only, but not the most stable one. And of course, the staggered form is the most stable one. And here what you can observe, the two bulky groups are away. Okay, that's what you need to remember. The two bulky groups are away in the staggered form. That is the reason this Newman projection formula is the most stable one. So this is about the butane. So now butane. So now let's look into the uh, terminology. It's called Kleine-Prilog terminology. So as per this classification of cycloalkanes, so you know that if the three carbon atoms are involved in a ring formation, it's called cyclopropane. So cyclopropane is the one belongs to the small ring. Cyclobutane means a four carbon atom is involved in a ring formation. It's called cyclobutane. The cyclopropane and cyclobutane are belongs to the small rings, and here these two rings are highly strained. Okay, so we will tell you what and all the strain we can found in a small rings. Okay, Then common rings. Common rings means 5-membered ring, 6-membered ring, and then 7-membered ring. So 5 carbon containing rings are called cyclopentane. 6 carbon containing rings are called cyclohexane. 7-membered rings are called cycloheptane. And these are called common rings. And here what is the obtained one is, it's a less strained one compared to the small rings. And the medium rings means 8 carbon containing one, 9 carbon containing one, 10 carbon containing one, and 11 carbon containing one. So 8 carbon containing ones are called cyclooctane, 9 carbon containing ones are called cyclonanane, 10 carbon containing ones are called cyclodecane, and 11 carbon containing one, and these are called highly strained. So large rings means 12 carbon containing and above are called large rings, and these are called strained one. So if we are looking into the more particularly one by one, so a 3 carbon containing small ring is called cyclopropane ring. In cyclopropane ring, so there is a bond strain. Okay, so there is a bond strain, there is a angle strain, so there is a Pfizer strain. Of course, there is also a Bayer strain. So because of these strains, 3-membered rings are highly strained. So 3-membered ring called cyclopropane ring contains bond strain, angle strain, Pfizer strain, Bayer strain. Because of this, a 3-membered ring cyclopropane is highly strained one, and because of strain, their stability is very less. So that means we cannot isolate it. Cyclopropane ring we cannot isolate, but it is possible to isolate triphenyl cyclopropane. So that is possible, and it is isolated, and it is also characterized. So cyclopropane alone, it is not possible to isolate because of this strain. So then we'll go to the next slide. Okay, so here what you can observe, a 4-membered ring I am taking. A 4-membered ring is called cyclobutane, and this is the planar one. And this is the planar one is unstable compared to the envelope form. This is called envelope form or puckered form. And here what you can observe, groups, okay? That's what you need to remember. So two conformations are possible with respect to the cyclobutane. So in the cyclobutane also you can find the Bayer strain, bond strain, and Pfizer strain is present in the case of what you call this particular conformer is called puckered conformer, and this is the planar one. That's what you need to remember. Between these two, this one is stable compared to this one. So that's what you need to remember. And so in the puckered form also, Pfizer and bond strains are present, but there is no angle strain here in this. But here there is a angle strain is present. So then if you are looking at a 5-membered ring, more particularly it's called cyclopentane. So this is the one is called planar one, and this one is called envelope one. And envelope, it is also called as puckered one, and here the puckered one will be the more stable one, and more particularly it's called envelope form. Envelope form is the more stable compared to the planar one. So let's go to the a 6-membered ring. So this is a 6-membered ring, and 6-membered ring is called what is called cyclohexane. So cyclohexane means we can look into the what is called as a chair form. So this form is called chair form, and this form is called board form. So you can observe that there is this here, whatever the hydrogen present here, whatever the hydrogen present here, so there will be interaction. So because of this hydrogen interaction, this board form is less stable compared to the chair form, and this one is called the twist board. Okay, twist board. Again, twist board is further unstable compared to the board form. So, and this one will be the half chair form. It's also called as envelope form. So, if you are looking into the, so overall from in cyclohexane, so chair form is the more stable compared to the board, twist and half chair form. When you are comparing these two, so this one will be the twist form will be the unstable compared to the boat form. Okay. So if we let us look into the energy profile diagram for the six-membered ring. So that is this. Here you can observe that a chair form will have a less energy. So because of less energy, so these chair forms are stable one. And you can observe that this is one enantiomer, this is another enantiomer. So these two are mirror images and these two chair forms are stable one. I think you are aware about what is called C1 and 1C, isn't it? This may be C1 and this may be 1C. Okay, I think you are aware that, familiar with that. So these two are mirror images, and these two are chair forms are a stable one. And why it is stable? Because they are having less energy. When you are comparing into the envelope form, this will have more energetic, and because of high energy, this is unstable. Boat form also having a little less energy compared to the envelope form one. And you can also observe that twist boat. Again, a twist boat is little stable compared to the boat form. So this is about the energy profile diagram of a six-membered ring, energy versus reaction coordinate. So now let's move on to the a substituted, a six-membered substituted compounds. Let's take 1,2 substitution, 1,3 substituted cyclohexane and their conformations. So let's take one. Before that substituted, we will look into the cycloheptane. Cycloheptane is also a medium ring. So this is the chair form one. Okay, and this will be the board form, chair form, board form, twist board. This is again twist board, and this one is the half chair. And here you can observe that the carbon atoms and hydrogens are very far. So because of this, this half chair form is the more stable one, not the chair form. In cyclohexane, chair form is the more stable, whereas in the cycloheptane, half chair form is the more stable one, because here the bond angle strain, bond strain, Bayer strain, Prelog strain, okay, Pfizer strain are less in half chair form compared to the other conformational one. So then let's take one more. So write the conformations of cycloheptane means you should write all these four, and you have to mention that half chair form is the more stable because angle strain, bond strain, Bayer strain, okay, Pfizer strains are less in this conformer, that you have to mention. So with this, I will go to the next slide. So next slide is about the more particularly conformational analysis of substituted cyclohexanes. Conformational analysis of substituted cyclohexane. So here I am mentioning that a chair form of cyclohexane, and this is the first carbon atom, this is the second carbon atom, and this is third carbon atom. Of course, this is the first carbon atom, this is the second one, and this is the third one. So whatever here hydrogen mentioned, one is called axial hydrogen. Okay, here axial hydrogen, this is also a axial hydrogen, so this is also a axial hydrogen. So there will be a interaction, this is called 1 comma 3 diaxial interactions. So because of this 1 comma 3 diaxial interaction, this moiety is unstable compared to the equatorial hydrogens. So why 1 comma 3 diaxial substituted compounds are unstable compared to the 1 comma 3 equatorial disubstituted compounds. So that time you have to explain that 1 comma 3 diaxial hydrogen interactions. So because of that interaction, these moieties are unstable. Whereas the equatorial, we won't find any such steric hindrance or interaction. So here there is no 1,3 interaction. In the only in the case of axial substituted ones, we'll have a 1,3 diaxial interactions. 1,3 diaxial interaction ones are unstable. Okay, that's what you need to remember. So overall, between axial 1,3 diaxial and 1,3 equatorial, 1,3 equatorial ones are stable compared to the diaxial substituted one. So if we are just looking into the enantiomers, okay, these two are mirror images to each other. So what will happen? So this can be converted into this can be converted into this. So it is estimated that 1 lakh times per second these two are interconverting. So 1 lakh times per second these two are, that means there will be a fast equilibrium between these two uh, conformers. Okay, and let's take here. This is called prelog strain. So what you can observe, at the first position there is a methyl group. So you know that at the third position there is a axial hydrogen. Here also axial hydrogen. Because of 1 comma 3 hydrogen and methyl hydrogen interaction, this axial methyl group is unstable compared to the equatorial one. So equatorial, when you are writing equatorial, so this moiety should come down and this should go up. So then only it's a equatorial one. This is the axial one. So axial methyl group and the equatorial methyl group. So when you are comparing these two, equatorial methyl group is the one is more stable compared to the axial one. So that's what you need to remember. Is it okay? So what you need to remember? You need to remember that axial substituted ones are unstable compared to the equatorial substituted one. Axial substituted one, there will be a 1,3 diaxial uh, interaction. Because of that 1,3 diaxial interactions, axial substituted ones are unstable, whereas in the case of equatorial, there is no such 1,3 diaxial interactions. Because of that, equatorial ones are more stable compared to the other ones. That's what you need to remember. Okay? So then what I will do, Okay, right. I think today 2 members are absent now. You just fine. So with this, let's go to the next slide. So next I'm taking a isopropyl group. So this isopropyl group is at axial position. So because a bulky group is in the axial position, there will be a interaction. What is that? 1 comma 3. 1 comma 3 diaxial interaction. So because of that, this moiety is unstable. So that is the reason what it will do. It will try to move towards equatorial position. The bulky groups are which are present in equatorial, such conformations are more stable compared to the other one. So that is the reason this one will try to move towards equatorial one. So equatorial isopropyl cyclohexane is more stable compared to the axial isopropyl one. That's what you need to remember. So here what I'm same thing only, no? No, it's a different one. So again, here the substituent is tertiary butyl group. Tertiary butyl group is a bulky group, and if this bulky group is present on the axial means such one is highly unstable. So that is the reason it will try to move towards the equatorial position. So here you can observe that is a equatorial position. So equatorial tertiary butyl group, and tertiary butyl cyclohexane is most stable, and it won't get back into a actual tertiary butyl cyclohexane. That is the thing you need to remember. So, but here in the isopropyl case, so to some extent it can get back into a actual one. But in the tertiary butyl, always this group is takes the position of equatorial one, and the equatorial tertiary butyl one is more stable compared to the actual one. So this is about the conformations, more particularly what is that substituted cyclohexane substituted conformation. We also discussed about the conformations of small rings. Small rings means more particularly a 3-membered ring and 4-membered ring. So similarly, we also discussed about the conformations of what is called as medium rings. Medium rings means 5-membered ring, 6-membered ring, and 7-membered ring. In a 7-membered ring, off-chair form is the more stable one. In a 6-membered ring, chair form will be the more stable. Again, if there is a substituent means substituents. Those who are occupies the equatorial position, so such substituted cyclohexanes are unstable, a stable one. Okay, so this is about today's class. Maybe we also discussed about how one can assign the M and P to the chiral compounds, and today we also discussed about the stereochemistry of cyclooctene. Okay, in that cis one is a chiral compound, and the trans one is chiral compounds. Okay, that's what we discussed today. Maybe what I will do, maybe I will stop at this stage. Maybe the remaining thing I will discuss in my next class. Okay. So now tell me, 2 members are absent now. Just tell me the name.